I would like to introduce while we set up, okay, perfect. Dr. Jim Bell, who will be presenting Curiosity and Perseverance rover missions. Welcome, Dr. Bell.
Good morning. Welcome to Arizona State University, my home institution. I'm a professor here, and it's delightful to have all of you here on our Tempe campus. So welcome on behalf of the approximately 150,000 students, faculty, and staff who are associated with this university. We're America's largest Tier 1 research university, and I think one of the biggest universities in the world. And we are deeply, deeply embedded in the Mars program. So I'm looking forward to meeting many of you tomorrow, late afternoon. We're going to have a little social event over in one of our buildings where we do a bunch of our space mission operations and fabrication testing, and give you some tours of what we're doing over there. We are actively involved in Mars orbiters, Mars rovers, lunar orbiters, asteroid orbiters, outer solar system missions, etc. And we've got a spectacular meteorite collection, the largest university meteorite collection in the world. And you'll see a lot of that if you come over to that building tomorrow. But it's just great to have folks here from the society and to host this meeting. I want to acknowledge my colleagues, Tiffany Rauch and Scott Smass, who helped James and others with some of the logistics here. So we're delighted that you're here. So I want to just update folks, speaking of active Mars missions, speaking of getting to know Mars, speaking of trying to figure out what's going on in this place so we can set the stage for the kinds of visions that you just heard from your visionary leader. You're a tough act to follow, Mr. Zuber. So I'll update you on what's happening with two of those active missions: Curiosity rover, which has been on Mars for more than 10 years now, and Perseverance rover, which is about a year and a half in to its mission. And we are actively working on the imaging systems and other kinds of work related to those rovers. Let's see, how do I advance here? Oh, here, like that. Yes, good. Okay, but first, just how did we get here? Remind you of this this beautiful chart put together by my colleague Jason Davis at the Planetary Society. 47 missions since 1960, 8 different nations and organizations, 10 successful landers or rovers on the surface of the red planet. I mean, pretty spectacular era that we've been living through. More than 40% of them have failed. So, you know, it's just a reminder, Mars is risky, even for highly advanced robotics. Mars is risky. It's the hardest place to land in the solar system. Today's story is about 2 of those 10, the Curiosity and Perseverance. Oh, be careful, don't end show. Curiosity and Perseverance rovers, about 2 of those, and it's of course about this enigmatic planet that Dr. Zubrin started to introduce you to, and that you all, more than most audiences in the world, know extremely well, right? It's a world of contrasts. Parts of Mars look like the moon with a thin atmosphere. There is an atmosphere. It's a thin atmosphere. It has a dramatic effect on our ability to land on the surface. Stop it. Here, do that. But also has had a rich and exciting geologic history, much like our own planet. Some of the largest volcanoes in the solar system, some of the deepest canyons in the solar system, ancient river valleys that flow through terrain that's billions of years old from the early history of the planet, and even places where modern water appears to be seeping out of the subsurface in small little gullies and valleys on the sides of craters. So there's probably a water table, an ice table. Who knows what's going on in the subsurface? but probably lots of analogies with Mars. So it's an enigmatic planet. We look at Mars today. It is cold, it is dry, it is lifeless as far as we can tell on the uppermost surface. But we think a lot about Mars a long time ago, right? And this is an extreme artistic rendering. We don't know if there were ever oceans on Mars. Dr. Zuber and I could debate on whether Mars was really a twin of the Earth, as he said. I think it was probably a smaller, younger, less mature brother, perhaps. But there was water. There was a thicker atmosphere. There was water flowing on the surface in rivers and lakes and streams, and perhaps oceans. It's debatable. There's lots of debate going on in the professional community about that. But it was certainly more Earth-like then, early in the planet's history, first billion or 2 years, certainly more Earth-like than it is today. And so what was that environment like? And as we heard in the last talk, did life appear there? Did life appear there? And is life still there? Perhaps in the deep subsurface, okay? So we try to get at those questions as best we can, because we can't go yet and tromp around on the surface with our rock hammers and our drills and our sampling devices. We can't go yet, although that day will come. I share Dr. Zubrin's optimism on that. So we do the best we can with these amazing robot geologists, like Curiosity, and like Perseverance, and like Ingenuity, little helicopter that was demonstrated on Mars last year, first demonstration of powered flight on another planet. So we use these robots as avatars for ourselves, and we equip them with mobility, right? And we've had mobility since Mars Pathfinder and the Sojourner rover back in '95, and the Mars exploration rovers, Spirit and Opportunity, in the early part of the 21st century. And we have mobility with these larger vehicles, Curiosity and Perseverance. And it's not zipping across the surface, okay? This is max speed here, 4 centimeters per second for a Mars rover. And that's really kicking up some rooster tails right there. But it is super important to be able to move, to explore the landscape, to go from one place to the next. That's what we will do when geologists eventually go out and do field work on Mars. So mobility plus all kinds of sophisticated science instruments, right? Laser chemistry tools, mineralogy tools, instruments to measure the current weather, instruments to take images and infrared spectra of the surface. And so these are very, very sophisticated laboratories, both Curiosity and Perseverance, both of them equipped to drill into the surface, and Curiosity equipped with instruments that can do organic chemistry measurements and mineralogy measurements with those drill tailings, and Perseverance equipped with instruments that actually are capturing the drill cores and encapsulating them and preparing them for eventual return to the Earth. So similar systems, but very, very different missions. They're both are in craters with really interesting materials inside, craters that used to be lakes. Gale crater has this enormous mountain that rises to actually higher than the rim of the crater itself. The entire crater was buried with sediments. They've been eroded away. We don't know where they went, where they are now, how you get those sediments out of the hole in the ground. Don't ask me, nobody knows. It's a big enigma. But these are sedimentary rocks in there that were deposited in a lake environment. I'll show you some pictures. And then similarly, Jezero crater was a crater lake, and there's a channel, an inlet channel in the west side, and an outlet channel on the east side. And the inlet channel topography is lower than the outlet, and it was ponded lake water with a beautiful, gentle delta deposited, sedimentary rocks deposited on the west, and another one in the north, by the way, several deltaic deposits. And so we decided to send Perseverance there to look for evidence of that habitable environment and capture evidence in samples to bring back to the Earth. Okay, so two similar spacecraft on very different missions to different places. So I'll just give you a quick update on what's going on with Curiosity. The white line is the traverse path from 3,626 or 7 sols now of its 1 Mars year mission, where the rover has completed 5 full Mars years now, which is super exciting. Traveling from the relatively safe to land on plains, winding through these big sand dunes, and now climbing up more than 600 meters up the slopes of this gigantic mound of sedimentary deposits. And very, very quickly on the crater floor, we found evidence of conglomerates, loose, rounded pebbles that are cemented together by iron oxides and other kinds of sulfates and cementing agents. Looks a lot like if anybody's ever broken up a basketball slab in your backyard or something, right? That kind of conglomerate. But these are rounded pebbles that have been transported down the crater wall through river action, rounded and deposited. And so very, very quickly after landing, we realized, yes, in fact, this was an ancient lake environment. We used that laser zapper to basically vaporize little pieces of rock and soil and get the emission spectrum so we can get at the elemental abundance, how much iron, aluminum, calcium, silicon, and all that. And so the geochemists can put that information together to understand the past environment. And then lots and lots of imaging, of course. And so the cameras here, a byproduct of some of the amazing systems that have come out of Malin Space Sciences in San Diego, taking high resolution and wide angle imaging from that mast, looking at a diversity of rock types, including places where we see lots of evidence that there was not just surface water, but groundwater, right? And sediments, sandstones, mudstones gently depositing on that lake floor. We don't know how long the lake was there, right? We don't have age dating tools that are useful like we would in the laboratory in the building you're going to see tomorrow, which is partly why we want to bring samples back to do that kind of age dating. But it was geologically significant amount of time, right? It wasn't a decade, probably wasn't 1,000 or 10,000 years. It was hundreds of thousands, millions of years that it took to lay down these sediments, and that the water was stable in that environment for a long time. Down here, we're seeing evidence of fresh water, and we see some evidence of clays and other kinds of minerals that form in relatively neutral pH. Curiosity was the first to drill on Mars. Kind of interesting, when you drill into Mars or even just scuff or scrape the surface, red Mars becomes gray Mars, right? Much of the redness is from the dust, which is deposited everywhere, or from very thin layers of oxidation in that not very oxidizing atmosphere, but has had a lot of time to work. So we get very quickly at the sort of primary kinds of minerals, and they're very similar to what comes out of the volcanoes in Hawaii or Iceland or northern Arizona here, the basaltic minerals, olivines and pyroxenes and feldspars, right? Those are the minerals of a typical terrestrial planet, and Mars in that sense is a typical terrestrial planet. We've been able to do that kind of interrogation of the subsurface, the shallow subsurface, now 36 times, including just a few weeks ago, number 36. This has been a real testament to the engineers who have figured out how to keep drilling despite some aging and failures of subsystems in the drill and other parts of the rover, but we're still able to collect these samples, bring them inside the rover, take them to the organic chemistry set and the XRD mineralogy set, and get lots of detailed information. That's been a tough ride. Those of you who have been following the wear on the wheels know that the wheels have been ripped up, still drivable, but the rocks are very hard. We're seeing a lot of hard basalts, angular, glassy materials that are just kind of tearing up the relatively thin treads. And we've had to turn the rover into a dune buggy, drive on the sand as much as we can without getting bogged down in the sand, but still able to travel those many, many tens of kilometers now across the surface. So now we're in climbing mode. The picture in the upper left was taken early in the mission from down in the plains, and the rover now, I don't know if you can see my cursor, but the rover now is up in these hills, in these buttes, winding its way through crossing transitions in the minerals that we see from orbit. So from sort of the basaltic, sandy plains of the crater floor into the clay-bearing materials partway up that tell us about that ancient lake freshwater environment, into a transition region where the clays turn into sulfates, and sulfates indicating more acidic conditions, and then eventually the dusty plain, the dusty hills up at the top loaded with oxides. We don't know if we'll ever make it to the top. We've only climbed about 600 meters out of that 4.5 kilometer possible ascent in 10 years, but we don't have to make it to the top. We're really interested in these deposits down where the water was and the transition between the watery environment and the dry environment. So just some nice examples of some of that groundwater, mineral-filled fractures, just like you find on the Earth, where groundwater is seeping through and interacting with the bedrock. So the views, I hope you're following the views online. It's just spectacular scenery, really mountaineering with this vehicle now that we're up in those slopes. And just yesterday, hope you saw the press release that JPL put out yesterday, reaches the long-awaited salty region. And this is not sodium chloride. These are magnesium and calcium sulfate salts. And we knew that we'd cross this boundary from orbit. We hoped we'd cross it someday. It took 10 years to get up there. Okay. But we think that this might represent a fundamental shift in the climate of the planet. Right? And so this is the test that's happening now. We know we were in a watery lake kind of environment down lower. At some point in time, this all dried out and the mode of mineral formation changed dramatically. And the planet became the anhydrous world that it is today. And we think we might be seeing evidence for that in this boundary. So just some of the most recent pretty spectacular views. So we'll be interrogating these slopes directly, looking for pieces of material that have shed out of different layers and analyzing them in great detail, including continued drilling. So the team put together this nice 10-year poster, 5 full Mars years of weather data. What's the current Martian climate like, environment like? What's the weather like year to year, Mars month to Mars month? Okay, we've got an amazing data set that's continuous now, and that can be extended back many, many Mars years into the past with the orbital data sets and other landed data sets. 28 plus kilometers of traversing, 600 meters of climbing. And we just started extended mission number 4. And the goal is, did the habitability, the evidence for habitability that we saw down low on the crater floor in the low slopes of that sedimentary mound, did it persist? Did that habitable environment persist through what were significant changes in the Martian climate? That will be Curiosity's mission for the next few years, testing that hypothesis. Meanwhile, right, Jezero crater, Curiosity's doppelganger, Perseverance, is on a very different mission. Yes, there's geologic exploration. Yes, we're looking for habitability and biosignatures in a similar kind of crater lake environment. The big difference is we're not just drilling, we're coring and caching the samples for eventual return to the Earth. So that's the big difference. Okay, launched in 2020, landed February 18th of last year. It's just about to turn Sol 593 in Perseverance's mission. So we're still in the prime 1 Mars year mission. We'll finish the prime mission in January and start our first extended mission in January to continue going on. Perseverance is here in the this map shows all 10 landing sites on Mars for reference. We landed inside Jezero crater with that beautiful delta, and there's kind of a zoom up on it here. I'm consistently amazed and delighted that our engineering colleagues at JPL and other NASA centers can get us this kind of accuracy to send a complex robotic vehicle to pinpoint landing precision to get very close to that delta. And they did a perfect job, and you've all seen the amazing movies and all that kind of stuff. Perseverance has followed the white path here traveling a little more than 12 kilometers, almost 13 kilometers now, landing just off the Delta front here, but we couldn't drive right to the Delta, which is our main target, because this big sandy area called Seta. So we did a little toe dip into it here, and then did a booked around there, and now we're up right on the Delta front here. And sort of following us along has been Ingenuity, doing its historic flights. The little exclamation marks here are places where we have collected samples and successfully cached them inside the rover. And as of this moment, we have 14 rock core samples, several atmospheric samples, and some witness tube samples that are designed to test organic contamination of the system. Hopefully you've seen all of the amazing vistas and panoramas. The team here at ASU, we operate the Mastcam Z cameras. We put these panoramas and 3D models and all that kind of stuff together that you've seen online. Hopefully you'll get to meet some of the operations crew on Friday. We actually are doing super early operations these days. The crew came in at 5 in the morning today. They're over there working now. They'll probably be done by noon or 1 o'clock. But it's been just a hugely successful imaging investigation, RGB filters, plus infrared and ultraviolet capability, zoom capability, 3D digital terrain model capability. We use the cameras as triage, right? We use the cameras as triage because we can cover enormous amounts of real estate in color and 3D and help direct the placement of the very expensive to deploy in terms of time instruments on the rover arm that are going to drill or directly sample the chemistry and search for evidence of organic minerals. From our landing site, we were able to see the front of the Delta several kilometers away and did an initial survey of that Delta front and started to already map out back in February of last year where we were going to drive to, which deposits we wanted to try to sample, and where we were going to drive up onto the rover. Being able to see this from the ground, right? The view on the right, the orbital view looking down from the ground, we see the layers on the sides of the exposed on the walls of the eroding Delta and Delta remnants like this one. This is a Delta remnant that's called Kodiak. Let's see, here we go. Yeah, and that actually was the subject of our first peer-reviewed paper that came out of the mission Science magazine last fall. We could see these beautiful layered deposits and cross beds, very representative of the kinds of things we see in deltas on the Earth, but also, and this was surprising, we were expecting to see gently laid down sediments in this deltaic environment like you see at the end of the Mississippi River. We also saw huge rover-sized boulders, rounded boulders, and jumbled up evidence of massive but violent flood deposits. So it wasn't just all gentle delta deposition. There were episodes of really extreme violence geologically going on there, and that's a puzzle, and we're trying to figure that out. But that was one of the first surprises of the mission. We were never anticipated that we'd have the chance to help make and record aviation history here with our team by taking Mastcam Z movies. The cameras can take video, taking movies of the historic first flights of the Ingenuity helicopter. Hopefully you've all seen this. It's very simple. Wright brothers moment, rise up, fight the wind a little bit, steady yourself out, twist, and land. This was back in April of last year. And lots of coordination had to go on with the helicopter team, which is an independent spacecraft separate from Perseverance. And we had to coordinate our efforts with that team. It looks like my slow motion replay. Oh, here it goes. Here's the cool instant slow motion replay of the landing. We did this at high resolution so the engineers could get some information on exactly how the system responded in its to landing. Another cool thing, unanticipated surprise, helicopter goes out of the scene to the right, comes back in, bringing all this dust. Just brought a whole bunch of dust with it. It entrains dust. The atmospheric scientists are using the helicopter as an active dust lifting experiment with a known forcing to learn about how dust gets lifted in the Martian environment. So that's pretty cool too. And the helicopter takes its own pictures and its own flight movies, and those get relayed back through the rover and eventually to the Earth. So drilling and coring, first time we tried, we actually came up empty. There was nothing in the bit because the rock turned out to be very crumbly and it all crumbled right out. So we kind of learned an important lesson there, sealed the tube anyway, and got a Mars atmosphere sample out of it and some little flecks. So, Mars gave us lemons, and so we made some lemonade. We learned a lot about the kinds of rocks we can drill into. And the second time we tried, we looked for something much more rugged, this rock called Rochette, which is probably a chunk of old lava. We abraded it, learned how hard it was, very, very hard, igneous composition, and realized we could in fact drill into it and successfully collect cores. And so there's the end of the core. We take the coring bit and point it at the cameras. We could see the core in there, and that's the actual bit held by a technician before launch that core is in. So we were able to get, we were able to get several on that rock, and we double sample for reasons I'll describe in a minute. We're able to double sample 4 different, what we think are basaltic and volcanic kinds of igneous rocks on the crater floor. These are going to be spectacular for radioactive age dating when we get them back into laboratories here. So 8 samples from the crater floor. Lots of dust activity inside Jezero crater. Again, a surprise, much more than was anticipated. And that dust and sand comes up onto the rover deck. It's more than a meter off the ground. That just hops around and gets really, really dirty and messy all over the place, and changes with time rapidly. But a great meteorological record right through a storm that passed right over. So again, the atmospheric scientists and modern weather people are having a field day with these data sets. So what's next? We were going to head for the Delta last fall. We arrived there last fall. We started sampling some of these materials and imaging them up in great detail. You see a lot of similarities with what we were seeing in Gale crater, very fine layering, spectacular examples of layered sedimentary rocks. We're able to drill into some of them, and we've collected our first Delta core samples this past summer. These are sedimentary sandstones, 2 of them there from that deposit. And then most recently, just completing a few weeks ago, 2 examples of finer grained sedimentary mudstones from those lower Delta deposits. So those are in the can, 14 samples all in the can. What's next? We're hunting for regolith. We're driving up to little dunes, small ripples like this, and looking for a good place to use the regolith capture capability. It's a special bit that captures sand and dust. And we want to collect a couple of samples of that to bring some of the famous Mars sand and Mars dust back to the Earth as well. So that's what's actually happening right now. This week and next week, we'll be doing that sampling. Then what happens? Then we transition probably in November or December to a mode where we depot a backup sample cache, right? We basically drive over to this place called Three Forks, which is a pretty flat area, and we're going to put a fraction of those samples we have in hand. This is why we were doubling them. So 1 from each of the rocks that we have down on the ground for a future mission to come get them if the rover doesn't survive until later this decade when those future missions arrive. This is our backup sample cache, just in case the rover itself can't deliver samples. And that's what Mars Sample Return is. So Perseverance is part of Mars Sample Return campaign. Perseverance is the sample caching rover, right? Those 14 samples in the can now. An Earth return orbiter from the Europeans, a sample return lander from NASA will get launched in or around 2028. Get sent to Mars. That sample return lander will be visited by Perseverance as the primary sample delivery vehicle. We've got the other half of the backup cache, plus all the new samples we're going to collect in the months ahead on the Delta and beyond. And those will be delivered by Perseverance if Perseverance is still alive to the sample return lander. If Perseverance is not still alive, that lander is carrying 2 Ingenuity class helicopters. They will go pick up the depot that we're going to deposit next month in the safe landing site and deliver those little sample tubes to the sample return lander. And then the Mars Ascent vehicle, a rocket on the sample return vehicle in sort of 2030-ish. We'll launch those samples back from Mars. They'll return to the Earth around 2032-ish, 2033. What could possibly go wrong? Well, I have learned not to bet against our colleagues at NASA and other JPL centers. Our engineering colleagues are doing just fantastic, spectacular things. Just put this up as a reminder of spectacular, fantastic things, how hard this is, and yet how much we've done, how far we've come. And Mars sample return has always been a decade away for the past 2 or 3 decades, right? Now it's a decade away, but it's actually happening right now. The samples are being collected. Some of them are cored and sitting inside the sample return, sample delivery vehicle, Perseverance. So I'll end with this slide and invite you all to follow along. Meet some of our ops staff over in the building tomorrow. Take some of the tours, learn about what we're doing to and on the robotic side to help pave the way for the kinds of visions for human exploration that Robert talked about earlier. Thank you very much.